Our next topic, our next speaker is Sa Wu from Hunan University. The title is Line Spectral for the Ackner's measure on two segments. Please.
Thank you your introduction. Good morning, everyone. Today I will talk about night spectra for the Arcnex measure on two segments. This is joint work with Professor Mihalis Kolonzaks and Lu Xishi. Let me start with a basic definition. Let mu be a Borel probability measure on RD. If there exists a countable set lambda, such that in lambda form an orthogonal basis for L2 of mu, then we call mu a spectral measure and lambda a spectral of mu. In particular, if the spectral measure is a Lebesgue measure restricted to the set omega, we call omega a spectral set. And here there are some reasons why spectral theories is interesting. First, spectra are often not unequal. For a classical example, the unit interval integer is a unique spectral containing 0, but for the square integer is a spectral but not a unique spectral containing 0. Second, there are many single spectral measures. Jorgensen and Peterson found the first single spectral measure. Then found the one-fourth quantum measure is a spectral measure with a spectra of this form. That is, the lambda is a spectral for the quantum measure, one-fourth quantum measure. And later, Dudke and Hausman show we can scale the spectra in certain way. Just is the PM10 lambda is also a spectral of one-fourth quantum measure. So the spectra can be very rich and complicated. And moreover, spectra depend on the measure type. 和赖 and Rao found, the spectra must be of pure type. This means it must be discrete with finite support, or absolutely continuous, or signally continuous. There is a classical density result by Landau. For the big measure, spectra cannot be too sparse, but for many single spectral measures, spectra can be very sparse. Now, a natural direction is to ask how does the geometry of the support affect spectra? For example, the nine segments are one-dimensional, so it is reasonable to expect that if a spectral measure is supported on the union of nine segments, then spectrum may also behave in one-dimensional way. That is, spectra is contained in a straight line. In here, if a spectra is contained in a straight line, we call it a straight line spectra. Today, I focus on the following question. Can we measure supported on finite union of nine segments? We ask, and what conditions is every spectrum a straight line spectrum? Let me first show an example that has a clean answer. Consider the Acknex measure mu. The measure mu supported on these two segments. One segment on the horizontal and another segment on the vertical. And the two nice segments are symmetric. The symmetric. Many papers studies this model. The final conclusion is this measure is a spectral measure if and only if it admits a straight line spectrum. So in this model, it has a clean positive answer for this question. So now we ask what happens for any two line segment in the plane. Here, this means given any two line segment in the plane, we ask when is the arcnex measure on the union of two line segment a spectral measure? If it is a spectral measure, must every spectrum be a straight line spectrum? So next, our goal is to solve these questions. So to solve these questions, we first need to normalize the two line segments. We can let I1 and I2 be two non-overlapping line segments, and the total length to be 2. And let nu be an arcnex measure on the two segments and divided by 2. So it is a probability measure. And then we can divide it into 3 cases to discuss it. Case 1, collinear line segments, and case 2, parallel but not collinear line segments. Case 3, no parallel line segments. For the collinear case, without loss of generality, we let the two segments live on the x-axis in this direction. So, and then let nu be an arcnex measure on these two segments. Some known results show that the measure nu is a spectral measure if and only if when the lengths of two segments here are equal, the lengths are equal, then the gap in here, the gap must be integer. When the lengths of the two segments are different, then the gap in here, the gap must be an even integer. Moreover, if the arcnex measure nu is a spectral measure, then it admits a straight line spectrum. The spectrum can become the x-axis direction. So in here, if the measure nu is a spectral measure, we ask does nu only have line spectrum? This answer is no. Here the segment in here the segment live on this direction is x-axis. So for any point in here, the second coordinate b does not affect orthogonality because this. So the vertical coordinate doesn't matter. So we can move spectral point up or down, and then it is still a spectrum. So the nu admit a straight line spectrum, but not every spectrum is a straight line spectrum because we can move the spectrum up or down. Now let's move on to the parallel but not collinear case. For the parallel but not collinear case, combining some result, we have the following theorem. we let L in here, L is a be a straight line through the orange such that the projection onto L is injective almost everywhere on the two segments, and then you be an organic measure on the two segments. Then you has a nice spectral measure. Then you has a nice spectral content in the straight line L. If and only if after projection, mm, after projection the next of the two segment, um, if 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 it is equal, the gap must be T1 plus T2 multiple of integer. If if the next if the next of the two segments after projection are different, the gap must be two times T1 plus T2 multiple of integer. So this means if we want to get a straight line spectral content in a straight line L, we only need to check if the next of the gap belong to this range, the radar part of the projection onto the L. Next, the proposition tell me we can show many good projection line for any k greater than 0. We can find a straight line LK such that the projection onto LK is injective on this two segment, and the next of the gap after projection is k multiple of T1 plus T2. In here the T1 and T2 are the next of the two segments after projection. So we record here. We know if the k belong to the integer, if T1 equal T2, we can take a straight line spectral. If the T1 not equal T2, we can take k in even integer. We can also get a straight line spectral. So for these two cases, there is a spectral number contained in a straight line LK. So we have the following theorem. If the two segments are parallel but not collinear, then the measure nu is always a spectral measure, and it have infinitely many straight line spectra through the orange because the k can take infinitely many values. Moreover, if we only care to show the existence of some spectra, then we can choose a straight line S with joins the left end point of one segment with the right end point of another segment. And then we can project the two segments onto the straight line escape. So we know the projection is injective and the gap is 0 after projection. So we look at this. If the gap is 0, then the 0 belongs to this range if T1 equal T2 and T1 not equal to the 0 also in this range. So we know for this, we know we have the measure has a spectral content in the straight line escape. So in here, we ask, does you only have nice spectrum? The answer is also is no. In fact, for the two equal-length parallel but not collinear segments, convex and light construct a spectrum that is not contained on any straight line. So there exists infinitely many straight line spectra, but not all spectra are straight line spectra. Now we go to the no parallel case. For the no parallel segments, we use an even transformation to transform the measure nu into the sample measure rho. The sample measure rho supported on these two segments, one segment on the x-axis and other segment on the y-axis. In here, the measure rho is an arc-length measure on just two segments, and we can transform the study of the measure nu into the study of the measure rho, and this even transformation keeps spectrality and also keeps the straight line spectral property. So in here, next we can focus on the sample measure rho. Now our goal is to describe when rho is a spectral measure and to study the structure of the spectrum. This means to answer are all spectra nice spectra. Next, we need to give some one-dimensional results. For the interval 0 to t, we know the spectrality identity is this form. So in here, in our setting, we need to change the constant on the right hand side to t times omega in here, in this form. In the proposition 2, the identity is this form. And then if the lambda is a discrete periodic multiple set, then lambda can be written as this form. That just means in here when look just mean the number of point in here, the lambda, the number of point is faced by the period. So if if the t equal omega in here, if the t equal omega, then the number of point in here is twice the period. And the lambda can be expressed as this form. If the t greater than or equal 1, this means the next of the interval is greater than 1 or equal 1. And if the lambda is a discrete periodic set and all elements are distinct, then the lambda must be the integer transform of the 2 points. Moreover, if the t greater than 1, the lambda must be half integer. This means the inhaled alpha can take 1/2. Now we will apply the result to the x-axis and y-axis projection of the two-dimensional spectrum. Thus, we define lambda x and lambda y are the projection of lambda on the x-axis and the y-axis. So we can get if lambda is a spectral flow, then the projection lambda x and lambda y satisfies this one-dimensional identity like before, like this form. And the lambda x and lambda y are periodic set and all elements are distinct. So we can use this theorem on the projection lambda x and lambda y. We can get lambda x and lambda y must be this small, and the lambda x lambda y must be the integer transform of two points. If we inherit the t1 greater than 1, then lambda x must be half integer lattice. If t2 greater than 1, then lambda y must be half integers lattice. Moreover, because the lambda is a spectral flow, so by the orthogonality condition, we have lambda contained in the zero set of Fourier transform of law. So we have the following orthogonality equation. We know the projection of lambda x and lambda y is this form. So we can put lambda x and lambda y into the orthogonality equation 1. So we can get the precise form of lambda is this form lambda. Let me explain the theorem. Use the following picture. This means for the spectrometric law with a spectral lambda and 0 in lambda, we can get the spectral must be live on the straight line y equal x or y equal minus x. And the spectral is the union of purple and blue point. In other words, it is a integer translate of 2 points along the straight line y equal x or y equal minus x. If the next of the two segments are different, this means inhale T1 not equal T2, then inhale the arc alpha. The R can take 1/2. So the spectrum must be half integer along the straight line. So inhale in the non-parallel case, every spectrum is a straight line spectrum and contained in the straight line y equal x or y equal minus x. Now we state the necessary and the sufficient condition for the spectrality. We show rho is a spectrometer if and only if T1 and T2 satisfy these conditions. Next, we show the idea of proof for the necessary. When the measure rho is a spectrometer, we know the lambda must be this form. So we can choose some spectral point in lambda and putting them into the orthogonality equation 1, putting in the above equation. So this spatial point put a stronger restriction on T1 and T2 to such that the T1, T2 satisfy these conditions. And then it controls the relative position of the two segments. Next, we will show the sufficient by the projection theorem. Let mu be the arcnex measure on finite union of nice segments. And let L be straightized through the orange such that the projection pylon to L is injective almost everywhere on the support. Then the mu has a spectral lambda content in the straight line L, if and only if the projection measure is a spectral measure. So here, if we want to get a straight line spectral content in a straight line L, we only need to check if the projection measure is a spectral measure. So for the sufficient, when the T1 and T2 satisfy these conditions, we can project the two line segment onto the straight line y equal x or y equal minus x. So we can get the projection is injective and the projection measure is a spectral measure by labo results. So by the projection, the theorem, we can get rho is a spectral measure with the spectral content in the straight line y equal x or y equal minus x. So in summary, we can conclude that for the arcnex measure, nu supported on the two line segments. Then nu is a spectral measure if and only if it admits a straight line spectrum. Moreover, in the no parallel case, it admits only straight line spectrum. So then naturally we ask question 2. If nu is an arcnex measure on finite union of line segments, not only two segments, and the nu is a spectral measure, we ask, must it admit a straight line spectrum? The answer is also no. Next, I will explain why the answer is no by using about projection theorem and the following theorem. The following theorem tell me if one measure has a spectrum on the k-dimensional subspace, and another measure has a spectrum on an orthogonal complementary subspace, then the coevolution has a spectrum given by adding the two spectra. This is a powerful way to construct a spectral measure in higher dimensions or more complicated support. So using this theorem, we can build some example to answer the question. We take 3 segments and choose an irrational number R. And then we let mu be an arcnex measure on the 3 segments. And then let nu1 is be an arcnex measure on I1. We know nu1 has a spectral number 1. And then we let mu1 be the sum of the 3 Dirac measure. We know the mu1 has a spectral number 2. Then we can also writing the mu as a convolution of mu1 and nu1. By the above theorem, by this theorem, we can get mu is a spectral measure with a spectral number 1 plus number 2. But in here, for any straight line arrow, we can project just segment onto the straight line arrow. We have the projection measure is not spectral measure because by the Kolonczak and the Lee and the multiple results we know if the projection measure is a spectral measure, then each gap must be multiple of the connects of the interval. But in here we have we let the we let alpha be a rational number. So the gap cannot be multiple of the common next of the interval. So the projection measure is not spectral measure. So by the projection theorem, we know that mu doesn't have straight line spectra. But in here, we know the mu is a spectral measure. We also have another example with four segments in here. Let mu be an arcnex measure on just four segments, and let mu1 in here the mu1 be an arcnex measure on just union of I1 and I2. We know mu1 has a spectral content in the straight line y equal minus x. And let mu1 be the sum of just two Dirac measure. We know mu1 has a spectral content in the straight line y equal x. And then the mu also can be written as a convolution of mu1 and mu1. So by the above theorem, we know mu is a spectral measure. But here in here there is no straight line arrow such that the orthogonal projection pi arrow is injective on just four segments. This means there is no straight line arrow such that the projection is injective on these four segments. So we know the mu cannot have a straight line spectra because a straight line spectra would force an injective projection. So just two examples show that there are some arcnex measure on three or more segments such that it doesn't have straight line spectra. So for two segments, every spectral measure admits a straight line spectrum. And for three or more segments, there exists a spectral measure such that it doesn't have line spectrum. And for three or more segments, we still need a basic control. We ask, how fast can an orthogonal set groove? In fact, if the support is essentially one-dimensional, then orthogonal set cannot be too dense. So in here, we prove that inside a ball of radius r, the size of orthogonal set grooves and most linearly. Now we show the result for QoS in here. The theorem tell me let gamma be a finite union of QoS in Rd, each of which is rectifiable and has finitely no zero next. And let rho be an arcnex measure on gamma. Then in any ball of radius r, the size of orthogonal set grooves and most linearly. In particular, uh, the sum-bound hold when gamma is a finite union of nice segments. Finally, we show this in a more general framework for authors David Regalo. We look at the definition of authors David Regalo. If there exist two constants such that for every ball we have the following equation, then we call mu a authors David Regalo of dimension S. Hence, for offers David regard measure of dimension S, we have the following theorem. Just tell me in any ball of radius are the size of orthogonal set, gross and most like RS. In particular, for cubes, it grown and most like R. For n-dimensional perihendrals volume measure, it grown and most like Rm. So, in summary, for the two nice segments, spectrality is equivalent to admitting a strong nice spectrum. In the no-parallel case, all spectra are nice spectrum. For three or more segments, spectral measure may exist without any strong nice spectrum. And the size of any orthogonal set cannot grow too fast. Its growth is controlled by the dimension of the support. Okay, that's all. Thank you very much for your attention. I'm very happy to take question.
Okay, thanks for South's talk.